Hello everyone, welcome to my course Formal Methods for System Verification. In today's class, we will discuss one case study of SAT encoding. In the last few classes, we have discussed about the algorithm behind the SAT solvers, where we gave one formula in proposition logic, and SAT solver effectively give you a output under which the formula is satisfiable, right? Or the input assignment to the variables in the formula under which the formula become true, right. So, that is the SAT solver does. So, today we will basically take the logic locking domain and specifically an attack on logic locking, where we are going to use SAT solver at the back end to get the logic keys, right. So, because it is a completely new topic, logic locking, I will introduce what is logic locking first, and then I will define what is the attack problem, and then I will discuss how SAT can help in solving that problem. So, those who are familiar with the semiconductor industries, you are probably know how the chip is being built, right. So, just to highlight that, you have a initially design specification. From there, people design team develop your SoC, right. So, most of the time what it does, they basically use some third party IP or part of the code. Suppose you are developing a mobile processor, maybe there are some camera processing unit or USB processing unit, those Verilog code is already available, right. So, you will take it from some third party who has already that part, and then you develop the entire thing and you integrate, you get your design. So, you get a system level Verilog code in register transfer level, right. So, from the specification, design team job is to do that. You write some code on your own, you take some of the IP which is already available and combine and get your Verilog. Then you need the EDA tool, right. So, the EDA tool is what? The electronic design automation tool. What effectively does, you design in the register transfer level, but you have to bring it to the layout level, right. Layout is basically which have a transistor level design which can be fabricated and you get your IC or integrated chip, right. So, this synthesis tool has a lot of sub steps. I am not going into detail of that in this course. You do the logic synthesis, where you convert this RTL design into gate level design. And then you do the physical synthesis to get the layout, right. So, I will just give you a little bit of idea here. Logic synthesis convert, you can think about your RTL design, you have some A plus B, but in the gate level design is a adder, you will get a gate level design implementation of the adder and lot of many other things. You do the technology mappings and all. In the physical synthesis, when you have this gate level design, you have to place each of the gates in the layout. You have to make the connections, which is called routing. So, placement, routing and clock tree synthesis and so on, you will get basically the layout. Then you do the fabrication and you get your IC wafer. You do all the packagings and all, you make sure that you test your design and you get your IC which will go to the market. So, this is the entire the semiconductor design flow. So, now what are the things is here? You can see here that you need the third party IC, you need the EDA tools, right. You need this fabrication facility, you need packaging facility, you need testing facility. So, the entire flow is quite costly, right. You cannot own everything. There are only very few companies have the entire process on their own. So, what they do, it is basically called they send it to third party, right. So, what is basically, it is called globalization of this process. So, what you can do, you do not develop your own EDA tool, you take it from some third party, right. You take this IP, you do not develop all the IP on your own, you take it from some other companies. Fabrication is done by some other companies, right. So, they will do the fabrication and give you the IC wafer. Packaging is done by another company. So, they are expert in packaging. Testing is done by another company, right. So, your product is not your product, right. You basically you take help from many other vendors to get the thing done. Only thing, your idea is yours, right. You try to develop something which nobody has done it. So, that something is the novelty in your entire thing, so that you get things quickly, right. So, this is the design flow or IC supply chain. So, what are the threats are here, you have to understand. So, as I mentioned initially, you have this logic synthesis tool, physical synthesis tool, right. So, this is the flow that I have discussed so far. So, now you are taking this IP from somebody. So, there may be some dishonest employee in this whole flow, right. So, they can take your design from you, right, and they can sell it to the black markets and all. So, these are the threats, right, in the supply chain. Some wrong insider who basically get access and they can basically use it for wrong purposes. The most important, so this you can somehow trust your own employees and all, but finally the layout what you are doing, you have to give it to the third party fabrication, because fabrication is the most costly part of it, right. You need billions of dollars to have the fabrication facility. So, you have to give your layout to somebody, right. And now there a lot of things happen because it is not under your control. So, the layout received the contract from the manufacturing and somebody can construct the layout in construction and then you can use it illegally. Or let us say there is no wrong employee there, somebody get this packaging thing and that is go to the testing facility, right. So, you are basically this OFR is going to packaging facility or testing facility. So, there may be some wrong employee here also who can take your physical chip, they do this depackaging, image analysis and they can construct the layout and from there they can get the your net list. This process is not so easy, you need lot of expertise, but we all have already seen that people can do this, right. Given a physical IC, somebody can do this to get the net list you have. So, this is the threats, right. So, you have threats everywhere, but the most important threats are coming from this fabrication facility, packaging facility and testing facilities, right, where you are giving your valuable things to somebody and who can exploit this. And what are the things can happen? Once somebody get this, so there will be IP piracy, right. Your IP will be sell in the black market in a much maybe half price, right, overbuilding. You order 1 lakh chip, somebody build 10 lakhs, you are selling the chip in $1,000 in market, they will chip in $500 in market, right. And because they have not invested anything, they get your entire intellectual property for free, right. They can insert some hardware trojan in your design so that your design does not work as per your expectation, or they can create copies. So, these are the threats, right. So, but you have to protect it, because you cannot say no, I will not give my chip to somebody, I will do the entire things in my own, which is not feasible as I mentioned because of the cost involved, right. So, what are the solutions? So, there are many solutions was proposed by the researchers. What is watermarking? You make sure that you have some unique stamp in your design. You do split manufacturing, you do not give the entire chip to one vendor, you give some part here, some part to another vendor and then combine, or you can camouflage. So, people once you do this netlist reconstruction, you all gets looking the same, right. You will not able to distinguish between what is AND gate, what is OR gate in this layout, right. So, this is called camouflaging. So, if you do this that protection is there, but the most widely used solution is logic locking. Okay. So, logic locking is basically you kind of lock your design and give it to somebody. So, even if you have that design, you cannot use it. So, this is the most widely used solution. Okay. So, it is basically allow the high underlying functionality of the design. Okay. So, let us understand what is this. So, this also says that logical locking is the only method that can thwart all these kind of threats. Okay. So, what is logic locking? Let us understand from a very layman term, right. So, you have a design, right. If somebody do this reverse engineering or any other things, they will get this netlist. If get this netlist, they can use it, right. They can use it in other circuit also, they can create other productions and all. But what objective is that I have to give this design to somebody in the layout form, but my purpose is I want to do something so that they cannot use it, even if you can see what is the design, right. And what is the solution? You basically lock your design with some keys, right. Let us say I have locked my design with 3 keys here, K1, K2, K3. And the value of the correct key is K1 equal to 1, K2 equal to 1 and K3 equal to 0. So, this is the value. So, if when you assign this value 1, if you give 1 and 0 here, this circuit behave exactly as this circuit, right. But if you give some other value, let us say you are giving 0, 0, 0 or say 0, 0, 1, for some input the circuit will give same output, some cases it will not, right. So, how many input cases the output will be different depends on the corruptibility impact of this log or this keys and all. So, that is not part of the discussion in today's class, but effectively your circuit will not behave exactly as your original circuit, right. So, this is the locking. So, they can reverse engineer, they will get this circuit, but the problem is that if they give some input ABC, they have to also give the input of K1, K2, K3 which they do not know, and expectation is that you give 1 1 0 so that for all possible input ABC there are 8 possibilities, output is same, right. But the problem here is that if there are 3 keys, you can trial and error, right. You give 0 0 0 and check whether output is matching, 0 0 1 for the key and all possible 8 cases, right, 1 1 and then finally you will one time you will give 1 1 0 and you will see, oh, for this for all possible input your output is matching, so I get the key. But the problem here is that if there are 3 input there, 3 keys is fine, but you think about any design which has 30 inputs, 500 keys, right, or 50 keys, 200 keys. So, the 2 to the power, so if there are 100 keys, there are possibilities 2 to the power 100. So, you cannot check for all possibilities, right. So, this brute force way of identifying the keys is not feasible. Usually the circuits are locked with 100 to 500 keys, right. So, no brute force method will work. So, people can use XOR gate to lock, right. People can use marks to lock, right. So, effectively for if you give the correct key, the actual value will go, otherwise some wrong value will go, or they can use LUT to lock or XOR gate to lock. So, there are many ways they can lock it, but that is not the purpose of design. Whatever the way you lock, circuit will malfunction if you do not give the correct key. So, I hope I am able to explain what is logic locking and how it is actually giving protection against IP piracy and overbuilding and other problem, or in a very layman term, how it is giving protection of revealing your original circuit to the attackers. Okay. So, that is the logic locking. People are happy that I have locked my design and you cannot use it. Even if you get this version, you cannot use it unless you know the original key, right, or the correct key. But attacker will not, attacker also try their own way of attacking this circuit to get this key value, right. So, remember you have this already, right, you from the reverse engineering you have already this circuit, the locked circuit. This circuit you do not have, right, this circuit you do not have, but this circuit you have, you know exactly what is the connections and whatever, right. So, you get the internal because you get the netlist, right, this is called locked circuit. But also what you can have, the original company have already produced the chip and selling in the market. So, you can get a IC of this chip, right, which is called Oracle, right. Oracle means what? This is a black box to you, you purchase from the market. What will happen in this circuit, not exactly this circuit, I would basically the Oracle is like this, you have the original circuit here, let us say this is the original circuit and key is also there, right. So, this key is inside and the key is coming from here and this is your output. So, from a user perspective you do not know what is the correct key, that is embedded inside the IC, right, they have connected securely there. So, this Oracle effectively if you give an input you will get an output. So, this Oracle can be used to cross check whether what is the correct output corresponding to one input. As I mentioned, you could have purchased this Oracle and try all possible input, but that is not possible because of the exponential search space of the key. But you can still have this Oracle with you, right. So, what attacker has, they have a locked design, right. The locked design is this one as I mentioned. So, where you have access to the internal one, you know exactly how the connections, where the keys connected, which are the keys value, what are the inputs. So, that part you already have, right. So, that is the locked design that can be obtained by reverse engineering the layout or IC. And for this the access, you can access the internal things, right, the internal connection gates and all. And the Oracle is basically, as I talked about, is a functional IP purchased from the market, which is basically a black box, right, where you can give input, you get the correct output. Okay. So, this can be checked for input output. So, the attacker can have these two things. And what is your objective? He want to identify the keys, right, he want to identify the key values. So, if he can identify, then what will happen? he can just assign this value to this keys, and you can use this circuit, because in that case this circuit will work exactly as the original circuit, and then they use it in the black market for IP piracy, overbuilding and all other problems, right. So, that is the attacker goal. So, they want to get the key values. Now, the question is, can I use SAT solver to get the keys, and that is where this particular thing is interested or related to the topic I am teaching in this course, right, the SAT solvers. So, let us try to understand how I can model this key identification problem as a SAT solving problem, okay, or rather how can I use this SAT solver internally to identify the keys, and that is very famous, called Boolean SAT attack. This was proposed by late Pramod Subramaniam in this very famous paper, okay. So, let us try to understand. So, what effectively this SAT helps here. So, what we do here, we try to identify this distinguishing input pattern using SAT solver, okay. So, that is the objective. Let us see how we can solve this, and how can I model that problem, okay. So, let us take a lock design. Let us say I have taken this design. So, this design is a D which has ABC as the input, and K1, K2 and K3 is the keys, which is also an input to the design, and output is Y, right. So, this is the circuit I have. So, I can write the equation corresponding to Y, which is very easy to do, right. So, what I can do, it is basically, you can think about that, it is AB, right. So, this AB is, so I can write the equation corresponding to this adder, which is AB, right, and then this is doing XOR with K1, right. Then I also have this is one part, this is done. So, this is BC. So, I have this is BC NAND gate, right. So, this is AB bar, right, this is NAND gate effectively, and then this is XOR with K2. So, this part is done. Then this is effectively AC, right, AC bar, which is this gate, this is getting XOR with K3, right, and then this is getting XNOR, right. So, this part and this part is basically doing XNOR, right, or then you can do this, right. So, this is this part complement, and then you have a OR here, right. So, then this OR is this. So, this is your Y, right. What I have just done, I just write the Boolean equation corresponding to this circuits based on the connections, based on the AND or XOR and all other thing, right. So, this can be converted into CNF using Seitin transformation, right. So, there is no problem about that. So, given a circuit, I can construct the CNF formula which represent the output of that circuit in terms of the inputs and keys, right. So, this part is well understood. But what I am to identify is the DIP, distinguishing input pattern using SAT solver. So, what I will do, I will do a very interesting thing. So, let us say this is my lock circuit, right, this is my lock circuit. So, this is the lock circuit. I will create two copies, okay, I will create two copies, lock circuit 1 and lock circuit 2, and so I is basically the input, right, ABC, okay, and K is the keys, K1, K2 and K3, right. So, what I will do, I will connect the same ABC to the both circuit, is basically I. So, I am just writing I here. So, here there are three signals effectively. So, I will give the same ABC to both values. I create two copies of this key, okay. One copy is called K1, the other copy is called K2, which is very simple. So, effectively what I will do, I have K1, K2, K3, right, there are three input. So, K1 is basically K11, K12, sorry 21 and K31. So, effectively I just add just 1 with all the keys, and K2 is basically K12, K22 and K32. Effectively I just created 2 copy of this variable, and what is effectively means, in this equation I, whatever the variable this K1, K2 and K3 is there, I replace them with K11, K21 and K31 for this circuit, and for this circuit the LC2 I will replace this K1 with K12, K2 with K22 and K3 with K32. So, this is what effectively mean, right. My output is Y1 and Y, so I will get Y1 and Y2, right. So, this is my called mitre circuit. So, in diagrammatically it is looking like this, but effectively what I will do, in this equation I will create a 2 equation. One is Y1 equal to the same thing AB XOR K11, right, then or AB bar or K21, right, then or AC whatever is there plus K31 this bar, right. So, effectively I just see this, I just add 1 for this, and similarly I will do Y2 equal to the same thing with K12, K22 and K32, right. So, this effectively this circuit means I just create 2 equations from this, right. Now, so this is my mitre circuit. What I am going to ask the SAT solver, you see, find SAT, right, or check SAT of this mitre circuit, right. Mitre circuit, say this is the mitre circuit, plus Y1 not equal to Y2. So, that is very important. So, this mitre circuit is nothing but these 2 equations. So, effectively write Y1 equal to this equation, Y2 equal to this equation. This mitre circuit is effectively means this, that I will write Y1 equal to this, Y2 equal to this, and I will also say Y1 not equal to Y2. So, effectively what this means, you find an input for which there are 2 different value of these keys such that output is different, right. So, here input is same and that input is called DIP, right. So, this is what the SAT call I will do. I am repeating again, I have given a circuit, I will create the circuit output in terms of the input and keys, some Boolean formula, I convert them into CNF using Seitin transformation. Then I will create a 2 copy of this, where I will keep the input variable name as it is, keys I will create 1 copy with 1 and another copy with 2 underscore 2 or 2, right. So, that there I will get 2 equation, and I will give these 2 equation to the SAT, and I will say ki you find a value of these inputs ABC and the value of K1, the 2 copies K1 and K2 such that the output is different, okay. So, that is why this input is called distinguishing input pattern, right. Why this is distinguishing? It is distinguishing these 2 key K1 and K2, because your output is 2 different. You are giving the same input to these copies, to these 2 circuits, and giving 2 different value of the keys, and for this keys I am getting 2 different output. So, this is the SAT call I am going to do, okay. But how I should use this information to prune the key search space, that is interesting, right. So, this is the role of SAT in this entire SAT attack, that given a circuit I will create 2 copies and I will just make a call check SAT of mitre circuit, which is the 2 copies, and I will say you find an input values of this input and keys such that your output is different. Let us say I got this, right. So, I basically, for my example, let us say I got in my input I is basically ABC, right, in my case, and K1 is basically K11, 21, K31, and K2 is basically K12, K22 and K32. The only difference is that I have added 1 here and here 2, right. So, once that SAT call return some, it is satisfiable, right. it say it is satisfiable. What does it mean? It will return the value of this ABC, K11, K21, K311, K31, K12, K22 and K32, value of this, right. Let us say I got this I is basically say 0, 0, 1. I am just giving a superficial example, right. And then I got this value is say K1 equal to say 1, 1, 0 and K2 which is effectively is say 0, 1, 1, right. I am just giving a superficial example. So, under this values, if I if you think about the log circuit it has A, B, C input, K1, K2 and K3 is the circuit, right. If I give this 0, 0, 1 here and the K1 is value say 1, 1, 0, let us say my output is 0, and if I give the value input is 0, 0, 1 which is this, and this key which is 0, 1, 1, let us say my output is 1. So, this is because this output is different, this must be 1 is 0, 1 must be 1, right. This is what we will get, okay. So, this is what SAT is ensuring to me, that for these values you will get two different value if I apply this input and K1 to the circuit and input and K2 to the circuit, okay. So, how can I use it? So, because this, if you think about the original circuit now, original circuit is something where you give I. So, this is the original circuit where input is only the I, right, and output is O. In my case O is only one value Y, right. So, if I give this ABC to this original circuit, what will happen? Say if I, so because ABC is the same values, right, 0, 0, 1. So, in this original circuit if I give 0, 0, 1 to this input A, B and C, I will get either 0 or 1, I will not get both, right, because it is circuit. Let us say I got 1, okay. So, let us say I got 1. So, what does it mean? It means, or let us say I got 0, okay. Say let us say I got 0 here. What does it mean? So, this key is definitely wrong, right, because for this key I am getting 1, but this key may be the correct key, okay, because I am getting 0, right, because it is matching with the oracle output. So, this is exactly I am going to do, that I call this SAT call, I am going to call this check SAT. SAT will return me the value of I, K1 and K2. I will take this I and I will give it to the oracle. I know what is the actual output, let us say that is 0, and here if I check, if I put this value to this log circuit, I will, one case I will get 0, one case I will get 1, right. So, the case where I get the 0, that probably the correct key, the other one I can remove, right. But interestingly I will not stop here. So, this is a layman work. Again if you do this, you are effectively removing only one wrong key. So, that will not help, right. What I will do, I will take that equation. So, the equation I have written here. That equation is say AB XOR K1, right, whatever the equation I have written here, K11. So, this Y1 equal to that equation I have written, right. In this equation I will put the value of ABC, okay, and the value of Y, okay. So, in this equation I am not writing again. So, this is this equation, the entire thing. So, in this equation if I know the value of ABC is 0, 0, 1. So, I will put A equal to 0, B equal to 0 and C equal to 1 wherever it occurs. If I put this in this equation, what will happen? And the output is 0 because I have already checked it. I will get an equation only in terms of the keys, right. So, effectively I will get an equation here which is Y1, so maybe it is 0, let us say this is 0 equal to maybe say K11 plus K12 plus K13 equal to 0, and let us say K and this is from the other one, the K12 plus K22 plus K, sorry I wrote it completely wrongly. So, there are two copies of it, right, which is K11 plus K21 plus K31 and this is K12 plus K22 plus K32, which is also 0. So, I am just going to add this to my previous formulation. So, this mitre circuit formulation what I have done here, I will just add this constraint. So, this constraint is not removing only one key, it is basically saying that this value odd will be 0, right. I am just giving this. So, there will be many input, many key combination that will be extracted, removed from this now. Okay. So, this is what I am going to do. So, then I am going to add this constraint to my previous formulation, which is this check set, and I again call the SAT solver. Okay. So, then what will happen? Now it will give the K1, K2 that also satisfy this constraint. It is not only satisfying the original circuit constant, I am also making sure that this K1, K2, K3 should follow these rules. So, the search space, if the entire search space is this probably remove this part, not only one key, there may be half of the keys is removed because of this constraint. So, next time when this SAT solver returning me this I, K1 and K2, it will return from this search space, right. Again I will get some value of K1 and K2 and some input, and from this input I will get the what is the actual oracle output, and then again I will get some constant like this, and that probably remove this part. These are the wrong keys. Then only key remain is here. Again I will get two such equation, and these two equation I am going to add to the original SAT formulation and I will call again. So, this way it is not removing only one key, rather it will remove a set of keys in every iteration, and finally I will end up having the correct key. In the last iteration what will happen? SAT will return unsat, it will say key unsat, because I do not have any two key values for which the output is different. So, that means for all input now the remaining keys always give the correct output. I do not have any scenario where there are two keys for which output is different, right. So, that time I got the correct key. I will just check what are the key remaining there, and I will just get that key. So, to get the remaining key I will just remove this part of this, and I will just set key, you give a check set of the mitre circuit plus all the constant that I have added, right. So, that will give me the key, and that is the correct key. Okay. So, the overall idea is like this: I create the mitre circuit, right. This is my mitre circuit, and I will give it to SAT solver, it will give me the DIP. This DIP I will give it to the Oracle functional IC, that will give me the original output, and then I will get set of equations from this lock circuit equations, where I replace all the input and output with the values, and K1, K2 will remain as it is. This I will again give it to the SAT solver, then it will give you another key, so it will basically remove the wrong keys. I add this to the SAT solver, and then again I go back and I do this, right. So, effectively I keep doing this and until I get unsat, that SAT solver say ki there is no such two key exists for which output is differ. So, that means all the key now left out is the correct key. So, that is the SAT attack. So, the very interesting is that it is a completely different problem, but that can be solved with SAT solver, right. And people have shown that for combinational circuit, even with 200 keys, 300 keys, we are able to break with SAT solvers. You think about that, which is practically impossible to do, to brute force check brute force wise that for 2 to the power 200 or 2 to the power 300 cases. Rather here, using SAT solver, I can prune out this wrong keys maybe in 5 iterations, 6 iterations. That is the beauty, right. So, you have the entire search space, probably you are adding few constant that will remove half of the keys, right. Maybe 2 to the power 100 number of keys are gone because of the constant that I am adding here, right. So, that is something very interesting, and this is how, this is a very perfect example of applying the SAT solver solving a practical problem. Okay. The same thing is repeating here. I will take a complete example, the same example that I have taken. So, this is my original circuit, this is I do not have, right. So, I will have this as a black box. If I give ABC, what will the output, I can check with this, right. This is my oracle, right. Internal thing I cannot check. So, this is black box. Only I can check input output, the internal circuit I do not know. So, this circuit I got, and from this I will write those equations, right. Y is in terms of that equation that I wrote, right, which is a function of A, B, C and K1, K2 and K3, right. So, this I can see the internal and get this equation. Now for this circuit, for explanation purpose, this is not how the SAT works obviously, this is just for explanation purpose. I am just seeing what is going to happen when I run SAT attack, right. So for this circuit there are 3 input ABC, and this is the input ABC. There are 8 possible values 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1 to 1, 1, 1, right, 0 to 7 values, because there are 3 input, 8 possible values. For this case, if you give this value to this circuit, you can cross check, the output will be this, right. This is the correct output or the oracle output. So if you give 0, 0, 0 to this circuit, your output will be 0. If you give it to 0, 0, 1, output will be 0. If you give it say 1, 1, 0, the output will be 1, and so on, right. So this is something is the original behavior. Now there are 3 keys, right, K1, K2 and K3. Again I am saying this is just for expansion purpose. SAT attack won't see this table, right, they will just handle the equation and try to give some input values, right. This is just for internal understanding what is happening. Now since there are 3 values K1, K2 and K3, there are 8 possible values 0, 0, 0, 0, 0, 1, 0, 1, 0 to 1, 1, 1. So there are 8 possible values. This I am saying K0, this is K1, this is K2 to this is K7, right. K0 means 0, 0, 0, K1 means 0, 0, 1, K2 means 0, 1, 0 and so on, right. Now if you since you do not know the value of this K1, K2 and K3, let us say you assume the value of K1 is K0, right. In this case, from this circuit you will get this output, right. Right. If you give to this log circuit K1 equal to 0, K2 equal to 0, K3 equal to 0, you will get, and if you give input 0, 0, 0, your output will be 1. If you are giving 0, 0, 1 to the ABC, to this ABC, your output will be 1. If you are getting ABC equal to 0, 1, 0, your output will be 1, and so on, right. Now in this case, that means if you give this K0, all the cases where the value is green is basically it is matching with the oracle. You see the oracle output is 1, this is also 1, oracle output is 1, this is 1. But wherever the box is red, output oracle output is 0, this is 1, oracle output is 0, this is 1, right. So all the red one is effectively the wrong output and green was the correct output. Now you see here in this log circuit, if you give K0, you do not know what is the correct value. If you are giving K1, K2, K3 equal to 0, 0, 0, 50% case your output is wrong. Out of 8, 4 cases output is wrong. If you are giving say K4, 3 cases our output will be correct and 5 cases output is wrong, right. Similarly, if you give K7, only 3 cases output is same and 5 cases output is wrong. K6 is the correct output. You see all cases output is matching exactly with the original output, oracle output. So your objective is to identify K6, which is 1, 1, 0, right. K6 is 1, 0, 0. So that is the correct output for this design, right. So this is your K6 and that is your correct output. Okay. So your objective is to identify this K6 for this circuit, okay. And again I am saying this table is not available to you, because your ABC may be 50, K1, K2 maybe there are 100 inputs. So you cannot construct this table, right. So this table is only for your understanding, okay. Now let us see. So in this case, so I formulate this mitre circuit which I have explained earlier, right. I will formulate that mitre circuit. I will create 2 copies, Y1 which is a function of A, B, C and K11, K21 and K31, and Y2 which is a function of A, B, C, K12, K22 and K32, right. And what is this function? It is basically the way you will get by just traversing this circuit and whatever the output you will get, right. So this I have already shown you earlier, so I am not writing the exact function, okay. So you basically construct this formula, you convert them into CNF and you just add Y1 not equal to Y2 and you just check SAT of this, right, and let us say SAT solver returns SAT, and it returned the value of this iteration 1 is basically, let us say it basically returned the value of ABC is 0 1 1. Okay. So, under this equation, if I put this value of 0 1 1 here, so what I will get? I will get, so I will put, let us say I run this using SAT solver and I got a SAT, and I got the value of ABC is 0 1 1. Okay. I got the value of ABC as 0 1 1, and I get some value of K1 K2 which is not important to me, because that is not a matter. What I want, this 0 1 1, and in this 0 1 1 I will put to this output, and I will get the output is 1, right. Now, what I will do in this equation, I will put A equal to 0, B equal to 1, C equal to 1 and Y equal to 1. Similarly, in this equation also I will put 0 equal to 1, 1 equal to, B equal to 1, C equal to 1 and Y2 equal to 1. So, then what will happen, this equation will become some function of K1, K2, K3, right. So, effectively this function will become this, this will become some function, right, function of K11, K21 and K31, right, some function equal to something 0, 1, whatever. This also similarly will become same thing, right, K12, K22 and K32, right. So, this is this equation will become, because I am specifically value putting the value of ABC. So, ABC won't work, I mean exist in this equation, Y and also does not exist, right. So, this will reduce to a equation of K11, K12 and K13 and this. So, then now next time what I will do, I will call SAT for this plus this plus this plus I will say Y1 not equal to Y2. So, what is effectively happening, I am saying ki all the value that does not satisfy this equation will not be considered again, right. So, then for this if you take this input, unfortunately only for K4 the value is different, right, because this is red, all are other green. So, for all other key will remain in this search space. So, if your search space was there, only K4 will be removed, right, K4 will be removed, because that is the only value which will not satisfy these two equations, right, because for this output is different, right. So, essentially internally SAT what it do, in a search space K4 will be removed, right. Next iteration, let us say it return this value ABC equal to 1 1 1, right. I will get output is 1, again I will put this value to this equation, I will get two more equation like this, and for this again I will add that two constant to this, and in this case K1 will be removed from the search space, right. Here the way I am doing it is not helping much, because in the search space only all the wrong keys will be removed for this corresponding input, but there is only one possible wrong key for this, which is okay, right. So, this K1 will also be removed. Again I call this equation, this equation, this two equation plus another two equation corresponding to 1 1 1, right. So, my formula size is getting increased. Again I am going to ask for check SAT of that combined formula. Let us say in this time it basically return 1 0 1 as the ABC value, and again in this case I will get the constant, and K7 will be removed, right. Again I am just removing only one value K7, right, this is going to be removed. Again I will add two such equations corresponding to these values, and this formula will grow again, right, one set of this, three sets of this kind of formula, that is reduce your search space, again it will call, and in this case say it return 1 0 0, but in this case I found that all other keys will be removed, right, only K6 will remain. So, in this case I will remove all wrong keys, right. So, every wrong keys will be removed, only K6 will remain. Next time whenever I just add this constant that 1 0 0 to these equations, I will get another two set of equation like this. Now, I have two original equations and four this kind of equations plus Y1 Y2, and if I ask SAT solver check SAT of this, it will say unsat, because there is no two key exist, only one key exists here, right, all other keys are removed, no two key exists for which output will be different. So, it will return unsat, and then I will just check for this. So, I will just remove only this part from this formula and rest of the things I will keep, and again I will just check SAT. then it will return K6. It will say that for K6 the value is same. So this is the SAT attack. So here it takes 4 iterations. There are total 8 keys, 7 are wrong. In 4 iterations it removes, right? But think about it all depends on SAT solver. If you would have decided in the first iteration itself that this is my DIP, it could have. In that case, in one iteration itself, I could have removed all the wrong keys, right? In one iteration, all 7 wrong keys are removed, only correct key will remain. Then in one iteration, I could have solved this problem. But in which order SAT solver will decide the DIP, it's his business, the way the DPLL algorithm works. But in some cases, the number of iterations may be 4, 5, but some cases it may be 1 for the same problem statement, right? But the important point here is that using SAT solver, I can get the key which is definitely correct because I am solving mathematically, right? So this I think is a very classic example of solving a practical problem with SAT solvers, right? I hope you understand the concepts. Thank you.